Your Holiness, thank you for joining us this afternoon. We are due to continue our investigation of physics this afternoon with a session that's called Quantum Physics and Its Implications. We will have talks from three speakers, Arthur and Michelle once again, and our good friend Thupten Jimpa will be our third speaker. And Arthur will start our deliberations, I think, by saying something about another fundamental theory in physics, this time relativity theory.
Your Holiness, the challenge of modern science is to think much more carefully and subtly about the world that we inhabit. And while there are many details, yes, carefully and subtly about the world, and while there are many, many details within physics, quantum physics, relativity, that are complicated, hard to understand, I think one of the foundational or most powerful concepts is that of context or relationship. This you see in every field that we take up, even in the simple illusion. Remember the big monster and the small monster? They were the same physical size, but they were in a different context. The lines were different, and so we saw the one monster as small and the other monster as big because of the context or relationship they were in. In Michel's examples also, he was at pains to say the moon was in a relationship to him as he went on his bicycle. And especially in quantum mechanics, this becomes very much the case. We cannot simply objectify the world. That's quite all right. Old friends need to greet each other. Again and again in modern physics, the danger is that we try, as we can in classical physics, to objectify the world. That is to say, to see the world as objects that are separate from and without any relationship to me. So the world is a world populated of objects in the world with no relationships. We see again and again that this does not work in the new physics, that it's a world filled with relationship, and we must remember ourselves and the role we play in constituting reality. Everything that appears in relationship, in a context. And so I'm going to work with you in this new area of relativity theory. But before I do, I can't help but remember how you played with watches. You loved watches and machines where you take them apart and you think all of the different parts and how they move, and then you put it back together again, and sometimes it even continues to work. Yeah? That you understand.
Oh, yes, I think very properly.
Sometimes it continues to work.
Sometimes wasn't.
Sometimes you didn't fix the watch. But I know that same feeling. I too loved to take things apart when I was a child and put it together again. The watch is in some ways, or the clock, is an archetype of the old classical physics. The way of thinking for a watch works for all of the world of the macroscopic, of the large things in our world. It's a very powerful way of thinking. But I believe that what we have in quantum mechanics, and especially in the new machines that are being built on the basis of quantum mechanics, is something which is not like the old clocks. It's like a whole new concept, a whole new set of concepts, a way of thinking into these new machines is required. And this is why it's so difficult. I think when we come back in our next incarnation, we will have to think these new machines, and the old machines will be like toys in the antique shop. So we now have in front of us this bold new challenge. The two sides of that challenge are provided by quantum mechanics and relativity theory. So I'd like to speak a little bit about the theory of relativity, what it says to us about the nature of reality, and especially, again, the importance of context and relationship. You know, Einstein loved a world, he sought for a world that was really existing. As Michel said, Michel felt, and I do feel also here, he was not correct in his longing for an old-style world. He was a person right at the crossroads of this new reality, this new way of doing physics. He says, behind the tireless efforts of the investigator, there lurks a stronger, more mysterious drive. It is existence and reality that one wishes to comprehend. And we all have that in our hearts. We wish to comprehend reality. But what is our expectation of how that reality will show up, you know? Now, I'm going to begin with a question concerning this idea of intrinsic properties that Michel introduced. I'm going to look at the same from the standpoint of relativity theory. You know, when you arrive in America, I don't know about you, but most foreigners, when they arrive in America, you have to give your fingerprints, you have to take a picture. They don't yet take DNA, but at some point they probably will take a DNA sample. So what they're looking for are so-called biomarkers that are a unique, enduring set of properties that identify you or me, that identify the object. So we know this object from that object. In the case of the biomarkers, they may look at height or weight, but these can change. You know, you and I can lose some weight, and then it's no longer the right measure. Eye color, gender, they're not unique. There are many people with brown eyes. But fingerprints and DNA, well, that's more or less unique. You could say this identifies the difference between each of us. So in looking for these unique set of intrinsic markers, we think we can identify an object. What are these markers in general? What are the fundamental intrinsic properties of bodies? Galileo, again, because he's one of my favorite philosophers and scientists, he made a distinction which nowadays we call the distinction between primary and secondary qualities. I'll explain more in detail what these are in a moment. So Galileo wrote hundreds of years ago that I think that tastes, odors, colors, and so on are no more than mere names, and they reside only in consciousness. Hence, if the living creature were removed, all these qualities would be wiped away and annihilated. Let's take a look at what these primary and secondary qualities are like. For example, color. Oh, you can't really see much. Maybe you can read it over there on this screen, not to the right.
Just for clarification, His Holiness was asking, you're actually talking about the reality of the secondary property themselves, not the whole framework of distinguishing between things and their properties. Because the separation of things and properties is a mental construct. This is in the Buddhist epistemological text that His Holiness was talking about.
Okay, this is, I think, a very important point. Yeah.
So, for example, a distinction is made in the Buddhist epistemological text, such as Dharmakirtis. We can attribute a lot of properties on a single thing. And some of these properties may exist by default in the thing itself. So, for example, a conditioned thing could be the fact that it is a product, the fact that it is impermanent, the fact that it is changeable. These are all natural properties of that thing. But we can then attribute many properties, from the point of view of our function. So, for example, so many of the attributes that we use in our everyday language are really constructs. And there's a beautiful verse in Dharmakirti's text where he says that the distinctions between things and their properties, the thesis and the evident proof, all of these distinctions, categories, are really categories that are skillfully created by the logicians, by the learned mind.
But they have no reality.
But there are, of course, other properties which are there by virtue of the existence of that thing.
Okay, so if I paraphrase, as I understand it, you have a thing and its attributes, and as you take away the attributes, you could ask, is there such a thing without any attributes, an attribute bearer that carries attributes but has none? Is there anything left? And you're saying that there are certain attributes, changeability and impermanence and so forth, which adhere to the attribute bearer, that which carries attributes.
Exactly.
And you're able to take away certain of these attributes, which are conceptual designations.
Exactly.
And there's something quite similar, actually, is part of the Galileo quote that I just indicated, because he says things like the color of the rainbow, the smell that we have of a cooked meal, the taste, the sound that you're hearing right now even, these are all conceptually designated. These are all secondary. So he's looking in his own way for a fundamental set.
Yeah, but these secondary qualities, even the animals must be able to perceive them.
Yes,
So
animals have them.
but they don't have concepts, they don't have categories.
Good point.
Size, shape,
These are the primary ones.
time 사진
The time also, it might be relative.
Time also might be relative. Yes.
Size, shape,
Size.
number. These are, I think, human mind. That's service. Primary qualities. Secondary qualities.
Yeah, but you're asking the right question, as I understand it. Are some of these what we call primary? Let's take length, size. Is it really primary, or is it also one of the secondary? What about shape or mass or even number? Are they really primary, or are they also part of the secondary? Are there any truly fundamental primary attributes? And if so, what might they be? And what we're going to do is not ask this as a philosopher, but ask this as a physicist.
So His Holiness would, pursue the following approach, which is to try to see which, how much of the properties, attributes can be perceived by, animals, the mammals that we share, and then these would be identified as primary, and how much of attributes require the human kind of mind and conceptual kind of, framework. We'll categorize them as secondary.
Mm-hmm. Well, here's then an alternate way of approaching this question. What we can do is we can say, all right, classical physics seeks to explain secondary properties, qualities such as color, in terms of primary qualities, such as size and shape and so on. All right, so we take the things which we experience in this hall, for example, all of the experience that we are having right now, listening to my voice, being in this beautiful hall, these are all secondary. From the Galileo standpoint, behind these secondary experiences, there are primary material objects, the light, waves, and so forth, that produce the sound, the light, the color, the experience. And he wants to explain the secondary in terms of the primary.
대단 저기.
And what we want to do is examine this
D
critically.
D star size, the D shape is low in
말해 니니가 캐주를 그저 가도다 저 상마 입다 상마 캐주 콘도 뜻이 아마도 유지키요다 대 가도다 대 입슬라고 그러봐 순항모대 캐주래 반항모대 캐주래 다 캐주 자와다 야라스
맞아. 디더 디 제요나 다다치기냐.
나래 no 되게도 so when you connect the two so the secondary qualities can be seen as arising out of
Arising from, that's
the
right.
primary.
They are caused by, they are stimulated by.
어.
Right? So the sound wave strikes the ear, produces a motion in the ear, that is then electrical signals go to the brain. You can say where, auditory something or other. Ocular nucleus, okay. And then somehow, this is the hard problem, we hear my voice and your voice. But we don't understand completely, but Christoph and others will try to explain that to us later. But the mystery is, from the standpoint of quantum physics and relativity, is are these primary qualities, any of them truly primary? You know? And so I want to ask that question and ask it in the context of not philosophy so much as physics. Yeah? So is there a world of intrinsic objects and properties, or is the world, you might say, intrinsically subjective, that the only world we know is the world of experience? And that if it's the world of experience, then it always has this subjective character. It doesn't mean it's not true, it doesn't mean it's false or something, but it always, I'm seeing red, I'm hearing sound, I hear it. Now I can have ideas about it being arising from, but is there ever a way in which I get past the experience to something other than experience? Let's take a look at this from the standpoint of not quantum mechanics, which works with the very small objects of the world, but with relativity theory, which is a revolution in our understandings of space and time and simultaneity and some of the most foundational and fundamental ideas of all of science. They unfortunately only become significant, these effects only become significant at very large speeds, very high velocity. When you went to CERN, you saw how big it was. Part of the reason it's so big and it has the shape it has is because of these relativistic effects, that they have to engineer that machine using relativistic engineering equations. If you engineer it the way you would engineer a classical watch, it would fail. So here's my little, I'll do one thought experiment. I'd like to do one thought experiment of the type that Einstein enjoyed, and it's the following. I have here a picture of a barn. I don't know if you have barns in Tibet or not, but it's... Okay, it has two doors, one in the front and the other one you can't see is in the back. And there's a pole that's below it, and they have a length. The pole has a length. If you measure it, I'm going to say it's a big pole of 25 meters long, so it's a long pole. The barn is only 20 meters long. And the relativistic challenge, the problem which the professor gives to his student, is to fit the long pole in the small barn so that you can close both doors at the same time, take a picture, and then you can open the back door and let the pole go out. Now, classically, that's just impossible because the pole is too long to fit in the barn. But believe it or not, and engineering proves this to be true in the CERN laboratories and so on, that pole shrinks as it gets going faster and faster relative to the barn. It'll shrink, in fact, so much that if you go at a velocity, it becomes shorter. It becomes shorter. If you go at 70% the speed of light, that's about 130,000 miles per second. That's very fast. 170,000. That's like 5 times around the world in 1 second. So from now to now, you'd have to run 5 times around the planet.
So you've got to open and shut the barn doors quite quickly then.
In order to keep the pole from crashing, you'd have to shut and open the doors quite quickly. Okay, but that doesn't matter. It's a question of principle, right? Can you shut the 2 doors simultaneously? Because that's what it means to be inside, right? Is when the 2 doors are closed together and the pole may be moving, and then you quickly open the back door so it can get through, right? So maybe you have a situation where the back door is closed, the front door is open, the pole comes flying in, you close the front door just for an instant, it's inside the barn, you take the picture, then you open the back door and the pole flashes out, right? Now, this seems like it would be...
고통을 조금 쉽습니다.
That's a thought experiment. But this is a thought experiment, though.
Yes, but the equivalent, you can't do it with barns and poles, but you can do it with small particles or atomic clocks and so forth. You can actually show that this experimentally works.
단지 thought experiment. 얘는 대단 차중보지. 얘는 quarks나 대도 다시 제도열에서.
All right, so this is meant to be a thought experiment, but then you can do a version of this in the laboratory. And everything you do to determine everything, whether the pole is in the barn, shows the pole to be in the barn very, very briefly, because it's going so fast. Now, this is a strange state of affairs. Because the pole was longer, now it seems to be demonstrated shorter. Now the second part of this thought experiment, and this is a hard one. If I have a pole like this, and I imagine this is the barn, and it comes through the barn, this will become shorter so that it fits in the barn and the barn doors can close briefly. Then it goes out the back open door. But from the standpoint of relativity, this is the same as moving the barn to the pole, right? So there are 2 ways of moving the pole towards the barn or moving the barn towards the pole. They look the same, right? So the question is, well, maybe the barn is moving and not the pole. Okay? So I'm going to assume that the barn is moving, right? It's the same whether it goes this way or this way. So now the question is, does the pole get shorter again? Or does the barn, which is in motion, become shorter? Einstein's laws, which he discovered and through pure thinking, no experiments, just pure logic and thought, say that any object which moves gets foreshortened, is made shorter in the direction of motion. So if it's the pole that's moving, it becomes shorter. If it's the barn that's moving, then the barn will become shorter. The pole remains 25 meters long, and now the barn, which used to be 20 meters, becomes 14 meters long. Will the pole fit in the barn? No, definitely not. There's no way you can close the 2 doors because the barn is far too small. The pole is 25 meters long, the barn is only 14 meters long. Okay, now, if you have scientists, one of them doing the first thought experiment, but in the real world, and another doing the second thought experiment, there's going to have very different opinions. One is going to say, I saw and I took a picture, and here is the picture, and the barn contains the pole, it's inside. The other is going to say, no, look, my picture shows the poles are outside the barn. And you come together in Drepung and you have a nice conversation with each other, and you get in an argument as to who is got a true state of affairs, who's showing the truth concerning the state of the pole in the barn. And Einstein will say both of them are true. Because what you're looking for is always in a context, a relationship. And when you ask what is the single true state of affairs, you're presuming that there is an objective view from nowhere. There's no person, but just a situation with its own truth. Not a truth relative to me or a truth relative to you, but a single absolute truth. And when we forget that relationship or context, then we come into great difficulties. If we remember the context, then when we come together, we will say, of course, given where you were standing and where the pole was moving, then you will see it this way. Given the fact that I was in a different reference frame and the barn was moving, then I will see it the other way. We will have mutual understanding because we understand the different contexts.
这是说说的呢。
This is a kind of profound result to me, because Galileo said length is objective. Length is a primary quality. It shouldn't depend upon my sense organs. Shouldn't depend upon me. I should be able to disappear. But in this case, what we're saying is that the vantage point, the viewpoint, is absolutely important to even something as primary as length, as size. In some sense, every property that you have on that list of primary properties is affected by relativity in this way. You must always make your measurements conscious of the fact that it is in context and in relationship. All of physics, quantum mechanics, we've just begun. There are many ways in which quantum mechanics gives the same lesson. You always have to bring the context and observer into relationship with that which is to be observed. And if you're looking for the absolute foundation, the real size, what's the true size? There is only the size relative to an observer. There is no true absolute size or true absolute weight, mass, and so on. It's always in relationship to a vantage point. So we have two views that are classically inconsistent. From a classical standpoint, they can't be. The view from the barn says the pole is inside. The view from the pole, where the barn is moving, says no, the pole is too long and it's not in size. So which is the true state of affairs? Both are true, but with respect to two different observers, two different frames of reference. One with the barn, the others from the pole seeing the barn in motion. And that which we took to be primary is now, can really truly be thought of as any length shorter than its so-called proper length. Yeah, I take this to have really great significance from the standpoint of the kind of considerations we have here, that each subjective account, each person who's giving an account will do so in a way that is completely consistent, where the laws of physics are all working perfectly. And in fact, Einstein showed that this is the only way that the laws of physics can actually be operating in each of the two reference frames with objectivity, with real success. So you're looking now at a situation where you could say simply from the standpoint of physics, we're discovering that we have to keep into account ourselves, you could say, the frame of reference of the observer. And you can ask whether there is any place, any frame, any reference frame, which is the privileged reference frame, and this is the search for the ether. Perhaps the ether provides a reference frame. Now we say there is no ether, so there is no preferred reference frame. Each person has the same claim to truth, even when they look to be opposite. Now there's a quote from David Bohm, your friend David Bohm, who I also knew very well and was also a great physicist, a person of extraordinary brilliance. I wish he were here. He would be a brilliant companion for this work. That in relativity theory, not only are lengths shortened, time actually can slow down and speed up, if you will, according to the motion. The relativity of simultaneity, that is to say, my two fingers are clicked simultaneous, but if you're moving, you'll see one first and then the other, move in the other direction, it'll go in the opposite. So that you take these three, length shortening, time slowing, and relativity of simultaneity, and that becomes the new framework for understanding the new physics. Bohm says, the analysis of the world into constituent objects has been replaced by its analysis in terms of events and processes. This is a to me, very powerful statement. We so much want the world to be made of objects like glasses and bowls and Kleenex boxes and computers. And that then on the microscopic scale, we think also cells and neurons and atoms and molecules, right? But what Bohm is saying is a very powerful statement, that this is a wrong view. Really what one has are events, things which arise, you could say phenomena, and processes, the way in which they evolve in time. And they give the appearance of objects of enduring nature. But what is more primary are the events, the phenomena, and their development. And for that, you always have a position, a subjective, if you will, element. I want to emphasize that this world is not a world of chaos. In fact, it is the ordered universe, right? People think, oh my gosh, between the quantum physics and the relativity theory, it's just going to be crazy, right? But in order to have a universe which is lawful, where the laws of physics operate, Einstein deduced these are the kinds of things which must be true, and then we check them out in the laboratory and we find, yes, they are true. So this is actually something of great beauty, of great harmony, of great possibility, and yet it's something which ties the reference frame, the place of the observer, with that which is to be investigated, so that the world is constantly arising from the two sides as phenomena. So here are what I think of as some of the implications. I think it's a wrong view actually to see and look for a single objective state of affairs. As Bohm says, objects are now being replaced. To think that there's just a single state of affairs that everyone will see in a consistent way is not the case. We have to understand the changes that are associated with context. There's what we might call a fundamental observer dependence. There's always a vantage point. There's always a viewpoint. It may be you asked about the dinosaurs, or back many billions of years ago. No human beings. And yet we describe the dinosaurs. We describe the earth. But we do so as if we were there with this consciousness, these eyes, these ears, and a news team, from Tibet News Company, with cameras that look from a particular vantage point at the situation. Then sure, then there would be a world that would arise. And it would look as they described, right? So you either have a real, you could say, observer, or an imagined observer. Then you've set the context. To take that observer and to forget them is a fallacy. It's simply just a forgetfulness. If we do this, we find, for example, that length is relative, and other attributes which we took to be primary are relative. Now, here's another one, which at least I think must be the case, that what I've just said has to be true at every level. It's not like you get to a certain place and then you break through to objective reality, absolute, right? That you have these same aspects which are based on relationships, these same realities are based on relationships that we experience. Now I have a picture here on the right-hand side. I don't know if you can see it well enough, but what it is, it's a picture of the globe of the earth resting on the back of an elephant. Now this is a story which comes from the ancient Greeks, because when they were trying to understand how the earth was supported, what was supporting the earth, right? So they said the earth must be on the back of an elephant. And then, of course, they were logical, so they asked, well, what's supporting the elephant? And someone said, well, there's a turtle.
Greek, yeah.
See a big turtle.
유럽 엘리펀트 왜 봐?
So there were no elephants in Europe, so how did they come up with that?
Oh, that's a good question. I think there were known to be elephants. Isn't that right, from Africa? Hannibal. They're not local, but they were known to be present through explorers and war and so on. Yeah. But good question. So the earth rests on the back of the elephant, and then you can ask, well, what does the elephant stand on? And the answer was a turtle. And then the person said, well, what does the turtle stand on? And after that, it was said, well, it's turtles all the way down. In other words, it's just, I don't know, it's the same thing all the way down. More and more turtles.
There is a similar origin myth in the Indian classical Vedic tradition. I think one of the Vedic texts, again, the earth is supported on the back of a turtle.
And then the turtle is supported on the back of another turtle.
So when there are earthquakes, that's when the turtle is moving.
I see. But the reason I bring this is not just because it's a funny story, but because we are always looking for the foundations or the objective reality behind experience. What is it that supports experience? We're looking for something other than experience to support experience. And I think this, on the basis of Einstein's work with relativity and the quantum mechanics, is not a good choice. It's a problem. That actually, when you look ever more deeply, what you find still are context-dependent relationships that give rise to phenomena that may be more and more subtle, more and more delicate, more and more fine, even almost hidden, but with refined instruments or consciousness, one can investigate them at every level. So that what one has is not turtles all the way down, but I would say this context-dependent experience that goes all the way down. And there's no need for any foundation other than that. What that means, though, is that we need to not just be stuck in one vantage point. If you're stuck in the vantage point of the barn, then you see everything from your worldview, everything from your side, then you fight for that truth. So I have a different picture. I have a picture of, let's say, a reality which you circle. You actually learn to take on the position and views of the other. So I should, even if I'm not a Buddhist, maybe Buddhist philosophy is interesting because it brings some thoughts which I hadn't thought before, a way of looking, a way of understanding. Maybe you get interested in physics or neuroscience, something quite different than what it is you were brought in, because it gives a fresh view into reality. And rather than trying to find the foundations of reality in an absolute, one moves around this circle, as I'm going to make a little movement here. So this is the scientist, philosopher, contemplative, making their way around the big questions of our existence. And with this, I'm going to conclude.
So,
the conclusion is that we need a kind of a comprehensive,
holistic
view.
Yes. Francisco Varela, who you know so well, for him it was the first person, third person, the inner science and the outer science. These are like different views around the circle. Some people now are looking at the second person. How is it we work in dialogue or across cultures with very different, sophisticated, but very different philosophies, to really live into the views of the other, so that we, through imagination and sympathy, we can change the context. We don't have to be born in Tibet in order to study Tibetan Buddhism. We don't have to be born where I was born and my universities to understand these questions. So we can teach each other, we can learn from each other, and by looking then from many vantage points, we come much closer to the, you could say, common understanding or insight that will be of help to us. Yeah. Okay?
Thank you.
Thank you.
Here we are. So my purpose this afternoon is to develop some of the consequences of what I've said this morning. One of the consequences is quite strange and difficult to accept to Western scientists. The problem is that usually when they have a physical theory, they wish to have a view of the world that goes with it. They don't just content with a theory that is efficient, that enable them to predict and to make technology. They want also to have a picture of the world. Einstein was one of these wonderful scientists who dreamt of a grand view of the world. But the problem is that quantum physics has put some obstacles on this way, and that presently there is no view of the world which is both compatible with quantum mechanics and which is uncontroversial, that everybody accepts, every physicist accepts, because each one of the proposed views of the world that fits quantum mechanics has paradoxes, difficulties. Nobody is completely convinced by it. So my proposition is that maybe we have to accept that this physical theory provides us no view of the world. So
View of the world. View of the world. No.
I think in Sanskrit you would call that in Sanskrit you would call that drishti. Drishti, isn't it? Now, I want to come back to basics, really to things, elementary things. So, what is science, actually? What is the purpose of science? It could be that science aims at giving us a faithful picture of nature, that it is a mirror of nature. This conception comes in two varieties. The so-called realist varieties, according to which a theory, a scientific theory, is a faithful representation of reality as it is in itself. This is the ultimate dream, in fact, of Western scientists. They want a picture of reality out there, but as it is in itself. The second view is more modest. It says, yes, a scientific theory is a picture of the world, but not a picture of the hidden world. A picture of the manifest world, the world which is visible, empirical world. And so empiricists say that good scientific theory is just a faithful summary of observed phenomena, not more. It's still a picture of the world, but a picture of the apparent world, not more. The second view of science is the other way around. It's not as if we were, so to speak, capturing nature in our nets, but it's us who are superimposing our concepts and our views on our image of nature. Kant was one of the proponents of this idea in Western philosophy, with some nuances, but I think I would skip nuances. The third possibility is what I would call here a middle way. It's, a scientific theory in this way of seeing it is neither a picture of nature, not just a superimposition of our own minds. It's the byproduct of an interaction between us and nature. It's the expression of an interplay between us and nature. And Francisco Varela developed such a view under the name of enaction. It is the theme of his wonderful book, Embodied Mind. according to him, there is no way of putting foundations, of saying that, in fact, we can ground our view of the world somewhere. There is what he borrowed from Buddhist thought, namely dependent arising of the knower and the known. So the interplay is what science gives. For instance, science can give us methods to behave adequately and efficiently in the world, namely to relate with the world in a very clear and efficient and powerful way. Nothing more. And so in that case, a scientific theory is only an instrument for us to orient in the world and use it in a mode which is useful for us. Now, second part of the basics. What is a physical theory? Namely, what is a scientific theory that bears on matter? Well, in fact, in the history of Western thought, there were at least 4 conceptions of what is a physical theory. The first, the oldest conception was the conception of Aristotle. He said that a physical theory is a statement of the first causes of every phenomenon. The first causes, namely, you cannot go beyond them, according to him. It's quite unlike Buddhism, because in Buddhism you can always find another cause which causes the cause, and so on and so on. But according to Aristotle, there was a first cause, and full stop. And physics should look for this first cause. It was also, physics, according to Aristotle, was also meant to find the essential properties of things, the properties that are most intrinsic.
그다음에 이슈 연구를 봐.
라,
네.
이슈 연결해.
에스코라스 연구는 이슈 연구를 봐.
연결해, 연결. 비슷해.
So, okay, but after a certain time in which this theory of theories was very much accepted, throughout all the Middle Ages it was accepted, people started to see something artificial in it. For instance, when somebody wanted to explain the virtue of the opium to bring sleep, he said, I can explain that by saying that opium has the essential property of being sleepy, And this sounds quite artificial. Okay, it gives sleep because it is sleepy. Okay, so people like Descartes, René Descartes, the French philosopher, said that this was indeed completely artificial and that you had to explain everything in terms of mechanical interaction, bumps of bodies one into the other, primary qualities, as Arthur told us, namely spatial qualities, extension, velocity, and full stop. Even the qualities, for instance, of the virtue of opium to bring sleep had to be explained in terms of motion of particles. This is what Descartes called a mechanical explanation. Among many other things, Descartes wanted to explain gravitation by way of bumping of particles into each other. For instance, he said that the gravitation was due to the fact that there was a surrounding of subtle matter that bumped into the Earth or bumped into us and pushed us towards the Earth. But then came Newton, and Newton went much further than Descartes on the plane of mathematical description of phenomena, but he had to relinquish any explanation of the type of Descartes. He didn't try to explain gravitation by means of bumping of particles into the Earth or into the objects that fall onto the Earth. But he explained
motion of celestial.
Celestials la nam la yobis. Celestials la nam ko kola la yodini tikite gamma ta. Terrestrials la sala yodini.
Okay. So Newton renounced explanation, mechanical explanation of gravitation, and he just posited a mathematical law This mathematical law was amazingly efficient to predict everything. You could predict all the motions of all the planets for 100 and even 1,000 years, and you were perfectly exact. Yet he had no explanation of gravitation, only a mathematical law. So apparently you have a sort of regression here. Before we had an explanation, and now with Newton we have no explanation. But we have a much better descriptive mathematical theory and predictive mathematical theory. Now, according to Bohr, quantum mechanics, for instance, is a good case of that. Physical theory is not even a description of phenomena. It's only of phenomena as they occur by themselves in nature. It is only a predictive tool, mathematical predictive tool, in order to predict what? Experimental event in the laboratory or technological event that you could deal with in your laboratory also, or in your workshop. Okay, so you see a sort of progressive decrease of the scope of theories, but a progressive increase in their efficiency. This is very fascinating. The more the theories are efficient, the less they pretend to make us understand the world as it is. Okay, now let's understand another point, another pedagogical point I want to make. It is often said that the interpretation of quantum mechanics is a problem. We don't know how to interpret it. So what is the difference between a theory and its interpretation? Now, a physical theory basically is a mathematical framework, especially according to Newton or Bohr, a mathematical framework to describe or predict phenomena. It is made of laws that connect variables. What is a variable? It's a value of a measurement. For instance, you can measure length, or you can measure velocity, and the value of the length you have measured is a variable. The value of the velocity you have measured is a variable. So a physical theory is made of laws that connect variables. For instance, classical mechanics is exactly of this type. It says this, a law of classical mechanics does the following job. It says, if you know, because you have measured, that position of this body is p0, and velocity is v0 at initial time t0, then under certain circumstances, you can calculate that the position and the velocity will be this and this later on. For example, if I tell you, okay, I've thrown this ball with this velocity, for instance, 10 kilometers per hour.
Speed, yeah.
Yes,
The
the speed,
okay.
yes. And then I throw it out from that point at the top of this tower, this metallic tower. Okay, if I throw it at 1.5 kilometers per second, it falls quite straight away towards the Earth. You can predict it with Newton's theory. But if I throw it much more quickly, then it becomes a sort of tour around the Earth. It becomes an orbit, you know. So here again, Newton's theory can predict that and describe the trajectory of the ball around the Earth. This is why it is so powerful and efficient. Now, okay, let's try to flesh out this mathematical skeleton. Namely, what is the view of the world that comes with this wonderful predictive and descriptive mathematical tool that enable you to predict the value of velocity and position from another value of velocity of position? In fact, there are many views of the world that fit that theory. There was the old view of the world of Newton, according to which the world is made of material bodies endowed with velocity and position. But there is also an alternative view that was formulated in the 19th century, which is completely different, which said, in fact, the world is not made of material bodies. In fact, the world is made only of energy. And sometimes there is a concretion of energy somewhere, and it gives rise to the appearance of a material body. This view was formulated by many scientists at the 19th century. Therefore, there are two conflicting views of the world that nevertheless fit the mathematical skeleton of Newton's theory. So you see that there is a difference between a physical theory on the one side, which is just a set of mathematical laws, and its interpretation, which is a view of the world. There can be many views of the world that fit this one mathematical skeleton. Okay, so this was the case with classical physics. It was no difficulty, actually, because each one of these views of the world fitted perfectly well, no problem. Only their multiplicity was a problem, because why many rather than one? Now, what is quantum theory? Next question. Oh, okay, I will skip the history because it would be long, but I would like just to tell you that in fact quantum theory is simple and understandable. Maybe that means that I don't understand quantum mechanics, but no problem. I accept that. Quantum theory is only a mathematical scheme to predict measurement outcomes with certain probabilities. You have, for instance, in quantum theory, a symbol which is very well known, the symbol psi, which was actually the wave function according to Schrödinger. So you have this symbol psi, but it is used for only one purpose. It's to calculate the probability of finding one event. Full stop. Yes.
Symbol
Now, once you have the initial function psi, then this initial function psi enables you to calculate the probabilities of the measurements at time 0, namely initial time. But you need also an equation that gives you the same predictions, not at time 0, but at a later time. And this is called the Schrödinger equation. Then, the Schrödinger equation modifies the psi function and turns it into another function that enables you to calculate the probabilities of the measured phenomena at time t. That is all that is to be known of quantum mechanics. Everything is in it, only the mathematics is missing. Okay? So,
His Holiness is wondering whether you've actually simplified it or made it more difficult.
I'm sorry.
Yes, okay.
I made it as simple as I could, but of course, it's quite difficult to go further, I think. Now, there are many interpretations.
Michel, just to go back, so your claim is that quantum theory is what? The essence of the quantum theory is simply this equation?
Yes, yes, exactly that. It's just, you know, a psi function that enables to calculate probability and an equation of evaluation of this psi function that enables you to calculate the probability not only at time 0, but also at later time. And that's it. Nothing more to quantum theory. Now, many other scientists, present scientists, believe the same type of thing. For instance, the Everett interpretation is very much similar to that. But I skip that. I don't care about that.
Galaxies 찍찍도 때문에 패시 왜 소리도
Naren.
다 전부 수준도 돼.
So in fact, if you look at
그런 아주 미끌왜
Naren.
왜 소리도
So if you look at sort of the cosmos from a vantage point of view, like the image, say for example, if you look at the Milky Way, there seems to be almost like a kind of a wave pattern there.
Yeah, yeah, absolutely right. Yes. Now, of course, this wave of which we are speaking is not a visible wave. That's the point. But it is an inferred wave that enables us to calculate many things. And therefore, since it enabled us to calculate so many things, Schrödinger believed that it was, in fact, an adequate description of reality, and therefore that reality was wave-like, was made of a deep wave, invisible, but causing many effects. The second interpretation is that, in fact, the psi function is just a mathematical symbol, nothing more, and it's just here to make us calculate the probability of presence of particles. And therefore, only particles exist, and psi is not just a mathematical symbol. So either the wave is all the reality, or the particles are all the reality, and the wave is just a symbol. And also there is a mixed conception, which was typical of De Broglie and Bohm also, which said that in fact there were the two things, half wave and half particle, that the particle was in some way taken by the wave, it was piloted by the wave, and therefore the wave was used by the particles to guide itself through the world. So you have these three interpretations, these three views of the world. Either the world is made of a wave, either the world is made of particles, and in fact the wave is just sort of mathematical symbol, and either there are two realities, half wave and half particles. Now, these three views of the world offer a lot of paradoxes. If you try to stick to them, you land into a lot of paradoxes. I just skipped the paradoxes because it would be too long and too complicated. I just realized it. But maybe there is a fourth possibility. A fourth possibility. This possibility is very challenging, but I offer it to you. It's that quantum theory says really nothing of the world, nothing of what the world is or is not. It just offers us a tool in order to orient ourselves by probabilities throughout the events that we meet or the phenomena that we meet in the world. Of course, it seems very counterintuitive. Quantum theory is an amazingly efficient theory. Everything here is based on quantum mechanics. Many elements of this computer are based on quantum theory. There are lasers. There are so many things that depend on quantum theory and that are so powerful. How is it possible that a theory that is not describing anything of the world is so powerful and efficient? It sounds strange, but I offer you a comparison. Let's take, the insurance companies. Insurance companies must know how many accidents there will be during the years to ask people the right amount of money to insure themselves against the accidents. Now, how do they do? Do they know which accident you will have next year? Obviously, no, not. They don't know the nature of the accidents you will have next year. But they use a powerful tool which is called statistics. And with this tool, which says nothing about the nature of the accidents, yet they are able to predict the number of accidents, approximately, of course, during the next years. It could be the case that quantum theory is this kind of theory, which is very powerful on a statistical level, and yet very weak on the descriptive or explanatory level. Okay, well, Heisenberg and Anton Zeilinger also were two people who were very close to this position. According to Heisenberg, you cannot say by means of quantum mechanics what happens in the world independently of your intervention, of your experimentation, of your observation. You can only say what will happen with a certain probability in the laboratory when you will observe it. And therefore, the verb to happen according to Heisenberg, the verb to happen is restricted to the observation. Nothing more. You cannot say more. You cannot say beyond anything beyond observation with quantum theory. According to Anton Zeilinger, who should have been present actually, quantum mechanics is a theory of the limits of available experimental information. It's not a theory of what the information is about. It's just a theory of information itself, nothing more. So, playing with words, I wish to offer you an attempted, very daring interpretation. Maybe quantum theory has revealed us that nature has no intrinsic nature. Maybe it's the true revelation of quantum mechanics. It's not a revelation about the nature of nature, but it's a revelation about the fact that maybe the nature has no intrinsic nature. This is a possibility. A very great challenge for Western thought. Western physicists have a tremendous difficulty to accept such views. They don't even consider that, very rarely. I could quote only 2 physicists, and most other physicists are very much against that. For instance, people say very harsh things against these strange physical theories, such as quantum theory, that apparently has no way to show us a view of the world. For instance, according to Isabelle Stengers, a Belgian philosopher, many physicists think that quantum theory has betrayed the ideal of science, because the ideal of science was to reveal the nature of things, whereas here it's silent. It cannot say anything, just say probabilities of events. René Thom, who was a French mathematician, was very, very aggressive against that. He said, in fact, quantum theory is the scandal of our century because it has betrayed the ideal of science. It's terrible. Okay, now, my personal view is that we must be quite prudent. Namely, should we go on with the ideal of science, even though it brings so much paradoxes, or should we drop the ideal of science, provided it gives us some clarity? That's the 2 options, I think. If the dream is suspended, much clarity comes. But of course, the dream was so dear to so many of our French scientists. Now, I think for Buddhists, it should not be a problem. For Western scientists, it is, but for Buddhists, it's not. Because, first of all, I would like to insist on the fact that maybe the reason why quantum theory is so powerful is precisely because it's not specific about anything. It's because it's so general. It covers all sorts of events in all sorts of domains, just calculating the probability of these events. One has showed very recently, it's a very recent work, 2 or 3 years ago, that quantum theory can even be applied to human sciences. It can be applied to linguistics. I could explain that to you later. It can be applied to semantics very efficiently. It's the same theory, and yet it applied to several domains. Why? What is the common point between microphysics and linguistics? The common point... The common point is that in both cases, you have relational phenomena. Only that. Only common point. Now, from a Buddhist stance, and I chose Dogen, the famous Japanese monk and philosopher. Very interesting. From a Buddhist stance, it's not necessary to go very much beyond what there is, what is immediately given, beyond the freshness of the quality of presence. You can, or you should, just appreciate suchness, tatata, in Sanskrit.
てこない。
What is given, immediately given, and not go beyond. And just describe what is given, maybe, but not try to imagine what is behind the veil of appearances. For instance, Dogen said, this entire universe has nothing hidden behind phenomena. There is no veil, no necessity then to remove the veil to see behind it. Just see the veil as it is present here. And what science does is exactly what Dogen described, namely unfolding these phenomena in the most profound depth, and therefore be able to describe them in the most precise way, but not go beyond it towards a possible nature of things. Okay, I think I will conclude on that.
Thank you very much.
Wonderful.
Your Holiness, I don't know whether you would like to respond to this, whether you agree with Michel that there is some similarity, some meaningful similarity here between his interpretation of quantum mechanics and the Buddhist philosophical tradition? This seems like a very big and bold claim.
Yeah.